Good morning. Today I'd like to introduce you to the concept of chemical equilibrium. Now this is just going to be an introductory video to chemical equilibrium. It's a very complex and often challenging topic for students to understand. So this morning I just want to give you an introduction to what is chemical equilibrium, how to write the equilibrium expressions, and just give you some basic oversight to get you started with the idea and concept of chemical equilibrium. So let's begin. This reaction here is often called the Haber process. It's the synthesis of ammonia from its elemental nitrogen gas and hydrogen gas. You notice here I've already got the reaction equation balanced for you. So this is representative of 1 mole of nitrogen gas plus 3 moles of hydrogen gas leads to 2 moles of the ammonia gas. Okay. Also notice on this reaction equation that we have double arrows. We have forward and reverse arrows here, meaning that this reaction will proceed forward to a point and then will start reversing itself. So we can have both reactions running simultaneously, both the forward, the synthesis of ammonia, and the reverse, which is the decomposition of the ammonia back to the hydrogen and nitrogen gases. And so what is chemical equilibrium? Chemical equilibrium can be defined as a state that occurs when opposing reactions, so opposing reactions are proceeding at equal rates to one another. So now opposing reactions, what that is right here we've got a forward reaction, the synthesis of ammonia, and then we have its reversal reaction. So we have opposing reactions happening in our system. Both the forward and the reverse reactions are occurring, and equilibrium is established when those two reactions are occurring at the same rate. So equilibrium is when opposing reactions, opposing reactions, I'm going to use RxNS for reactions, opposing reaction have equal rates. Now I'm putting rates in caps here because I want you to remember that it's when these opposing reactions have equal rates, not when the compounds or the elements have equal concentrations. Not when they have equal concentrations, but when the opposing reactions, the forward process and the reverse process, are happening simultaneously at equal rates of reaction. Equal rates of reaction. That's when chemical equilibrium is established. Now, when we look at these substances here, with chemical equilibrium, often what we want to do is we want to write what's called the equilibrium expression. An equilibrium expression is just a ratio. Just think of it as a ratio of the substances involved. It's a ratio, and this was important because there's this statement in chemistry called the law of mass action, developed by Waj and Goldberg. And the equilibrium expression helps us see the relationship, the relationship between the concentrations of the reactants and the products at this equilibrium state, at this equilibrium establishment. So Waj and Goldberg came up with the law of mass action, and it's the idea of writing the equilibrium expression to see that relationship between the concentrations. And I keep saying that word concentration because, again, it is a concentration value, not a grams, not a moles, Okay, we can flip from concentration into moles and grams really easy. No trouble at all using some simple stoichiometry conversions. Okay, so for an equilibrium expression, the first thing that's most important for you to remember is that you have a balanced reaction. Okay, let's make sure that our coefficients have been put into place so that we have a balanced reaction. Okay. The second thing I want you to remember when you get ready to write this equilibrium expression is we are looking at concentrations. Okay, so with concentrations, what we are referencing is molarities. Okay, molarity values. Molarity, just to review, is moles of solute per liter of solution. Okay, we are looking at molarity values once this equilibrium has been established. Okay, the third thing to remember, okay, is that in the equilibrium expression we exclude. Okay, we exclude pure solids and pure liquids. Okay, so in our reaction equation here, notice that we've got the states of matter for each of our elements compounds here as gases. That's what they exist as. So we need to take a second look at those when we get ready to write this expression, because we want to exclude the pure solids and pure liquids from our expression. Okay. Now, you might be asking yourself, why do we exclude pure solids and pure liquids? Go back to number 2. In the expression, concentrations of our substances are being expressed. Okay, that's the ratio, concentrations. Do pure solids and pure liquids have a concentration? Do they have a solute? Do they have a solution? Is there a solute and solvent defined? If you're pure water, then who is the solution made of? Well, there's no solute solvent defined, so there's not going to be a concentration value, so to say. There's not going to be a concentration change over the reaction. Okay, there won't be a concentration change because we are not using a solution of that particular substance. So we want to exclude pure solids and pure liquids from our expression. So now let's write the expression. Okay, so our equilibrium expression is equal to, we often use a capital K, and you'll see a subscript C for concentration. Sometimes you will see individuals put a capital K with a subscript of EQ for equilibrium. That's fine. They're often used interchangeably. And this expression is a ratio of the concentration of the products. Okay, and with concentrations we define them by square brackets. So ammonia is a product. Okay, notice I'm using square brackets to define molarity, okay, to help me remember that. And we use the coefficient from the balanced equation as our exponential value over the concentration of our reactants. So it's always going to be products over reactants. So here we have N2, okay, the concentration of it, and its stoichiometry is just 1. So if you wish to put it there, you can. Okay. And then the hydrogen gas concentration with an exponent of 3. Okay, so that is what we define as our equilibrium expression. Now, I want to say this, and I hope that you understand what I'm saying, is this equilibrium constant expression, this expression right here, depends only on the stoichiometry of the reaction. It does not depend on the reaction mechanism. Okay, it does not depend on the mechanism. It depends only on the stoichiometry of the reaction. And one final note, this expression is also dependent upon the temperature at which the reaction occurs. If we change our temperature conditions, then we would influence our endothermic, exothermic properties, and we would get a different ratio of our products and our reactants. Okay, so this expression depends only on the stoichiometry of the reaction, and the value of the expression is also dependent upon temperature. Okay? There's a second equilibrium video that will do a calculation, but in this one I just want to give you an introduction to what is chemical equilibrium and how to write an expression.